Hello everyone. In this chapter, we will study the motion of solid particles in a disk. Solid particles interact with gas in a disk and change the orbits around the protostar. I will show a solid particle loses the angular momentum and migrates toward the protostars. First section is a gas drag laws. Second topic is a motion of a particle in a disk. Last topic is a migration of a particles. First topic is a gas drag law. Gas rotates around the star with a slower velocity than the particles. So I write the equation of motions for the gas and solid particles. For the gas, centrifugal force is balanced with the sum of the pressure gradient and gravitational force. Gravitational force Gm substance over R squared is balanced with the two force B theta square over R centrifugal force and pressure gradient minus 1 over rho round P round R. And for the particles, two forces are acting on the particles. Gravity of the Gm substance over R squared and centrifugal force B theta square over R. These two forces is balanced. So from these equations, you can recognize the difference is a pressure gradient. Pressure is a decreasing function of a distance from a protostars. So this term becomes a negative quantities. Rotational speed of a solid particle is larger than the rotational velocity of gas. So due to such a difference, drag force is acting on the particles in a disk. So in this practice, calculate the velocity of a particles relative to gas in 1A use in the Hayashi model. Use the following equations of motion for a particle and gas. So first equation for the motion of gas and the second equation of motion of the particles. So second equation quite easy to solve. So we start with the second equation. Theta can be calculated square root Gm substance over R. Then you can substitute all the value. Mass of a star is the mass of the sun. And the distance from the star is 1A use. Then you can calculate it becomes 2.98 times 10 to 4 meter per second. R equal 1A use. This is minus 1 over 2. And the mass of the star is a solar mass. Then 1 over 2. So about 30 km per second is a rotational speed of particles. Then we'd like to calculate rotational velocity of gas. B gas thetas can be calculated Gm substance over R plus R over rho round P round R. Then take a square root. Then this part, first term exactly equal to this one. So we name it, this is V sub k. This is Keplerian velocities. This one is a V sub k square root 1 plus rho V sub k squares over R round P round R. Then we'd like to change the second terms. C squares over V sub k squares. And then rho C squares over R round P round R. Rho C squares is exactly equal to the P. Then this equation is expressed C squares over V sub k squares round log P over round log R. Then this part can be expressed with the scale height H over R squares. So is expressed V sub k square root 1 minus ietas. Ieta is a function of R. So ieta is expressed minus H over R squares round log P round log R. In the Hayashi model, P is a proportional to the rho times t. And the rho is densities at the midplanes is proportional to the r to the minus 11 over 4th. And temperature is r to the minus 1 over 2th. So this means r to the minus 13 over 4. Then you can find that this minus 13 over 4. 13 over 4 h over r squares. Then it becomes 4.0 times 10 to minus 3 r over 1 AUs, 1 over 2. So this is a value of the EATAs, and the rotational velocity of the gas can be calculated V sub k times the square root 1 minus EATAs. Okay, this is the answer to the practice 5.1. Migration of particles. A particle loses the angular momentum and migrates toward the stars. So we consider particles in a disk. The specific angular momentums is expressed angular momentum per unit mass r times rotational velocity of v. And the rotational velocity of v are Keplerian velocities gm substars over r. Then you can substitute this v into the here. The specific angular momentum is expressed g m substar times r. So angular momentums is increasing functions with a distance from a central stars. Then angular momentums has directions. So this is r and this is a v. The angular momentum is directed toward us. Okay, this is the direction of the angular momentum. Rotational velocity of a gas is slower than the rotational velocity of a solid particles. Then gas drag is acting on the particles. This is drag force acting on the particles from the gas. Then torque. You can calculate the torque. Torque N can be calculated. R cross F drag. This torque is acting on the opposite directions with respect to the angular momentums. dl dt is expressed N equal to the torque. Then L is decreasing due to the drag force because the torque has the opposite directions with respect to the direction of the angular momentums. And this leads to the migration of particles. Then to find out the migration speed, we need an expression for the drag force on the particles.